So Dave Buckler is our speaker tonight. Most of us know who he is. Um, he and his wife, uh, Lorraine, moved to Georgia. What is it, about 4 years ago now? I want to
3.
say 3 years
Yeah.
ago. And he was a founding member of the club, having been both outreach coordinator and president. And as outreach coordinator, he had incredible numbers of items, scientific items, some not even related to astronomy, which we set up at schools and other events. So he was also president for some time. He pioneered our annual star party at Plumas Eureka State Park. Following a career in science, which included 9 years at Lawrence Livermore Lab, he taught electronics and physical science at Yuba College, and he's authored a number of textbooks and lab manuals for Pearson education publishers. And I know that Dave worked a long time on this, and I think that hard work will show in this talk, as he usually gives fantastic talks. And we're looking forward to hearing from him. So let's welcome him on Zoom.
I wanted to start with giving you a little bit of background on what I was trying to do here. My original intent was to update what was going on in astronomy. And so I started with everything since my last Moon Dreams 1, which was 2015. There's a bunch of people that I left out, et cetera, et cetera. So I went and looked up some astronomers, and as I was doing that and reading things, I decided there were some authors I should bring up. So it wound up being authors and astronomers. Mostly I'd like to focus on what the astronomers have been finding, but I want to bring up a couple or 3 books along the way. So that's my intent. It was a little bit tricky to try to tie everything together into a coherent story. I hope it's coherent. We'll see where we're at on that. Okay, this was a quote from me. The moon is essential to human life. I think that's kind of one of the points that I wanted to make in this talk, so that we could see how important the moon really has been to human existence. So starting with a time perspective, I borrowed the idea from Bill Hartmann, who's been helpful on this presentation. He uses a calendar approach to time, and I thought it kind of helps the visualization of how long ago things were. To look at it this way, each box there represents 100 million years. So we have the sun's beginning on the upper left and where we are at the bottom right. And the sun was about 4.5, we say giga-years or billion years ago. A giga-year is a billion years. And so 100 million years seems like about a day in the overall month. There's 4.5 days or 45 days shown here. Now we break up the yellow area into 1 million year segments. Each box now represents 1 million years. And if you go to the bottom right corner, now we're looking at each box there now represents 10,000 years. So if you take the very smallest right-hand corner, that would include everything from the Egyptian pyramids and earlier. And most of human existence would be in that whole bottom row. So it looks like, in the big scheme of things, astronomy-wise, makes this look pretty small. I think that's true of almost anything you can say about astronomy. But time-wise, we haven't been here very long in the big scheme of things. Let me start with the authors. The first author I chose was Rebecca Boyle. She wrote a book which is new this year, 2024. And I think she did a really commendable job. She's not an astronomer, but she's a technical writer, has written for Scientific American, other publications, but this is her first book. And I thought she brought up a lot of points that I thought were of real interest. One of them is in this book, she started off with how the moon was made, and she talks a lot about evolution of the species, how fish started to walk, and they were basically ancestors to the dinosaurs, and possible changes that were happening to the Earth's obliquity, the angle that it makes, the tilt of the Earth, let's put it that way, and its effect on climate. And then finally, she wraps up with quite a long bit on history. Some of the history includes some stuff I hadn't been aware of, even though I did the 3 ancient astronomy things. I'm going to talk a little bit about a couple of things she brought up in history. So I'll move along with that, but the included the earliest drawing of the moon that she's got in there. One of the areas that she talked about were recumbent monuments or stone circles. They're located only in the northeast corner of Scotland, an area called Aberdeenshire, which is not a county, but it's a large area. It includes several counties in northern Scotland. And these stone circles are unique compared to Stonehenge, for example. And I had talked about stone circles in my first talk on ancient astronomy. So recumbent circles always have a recumbent stone, which is the largest one, seen in the picture here on the left. And it's on either side of it are 2 flankers. And the flankers, there are certain alignments, like on this one, stone 4, these are numbered clockwise, starting with the rightmost flanker. So that's, counterclockwise. The rightmost one is stone 1, the recumbent stone is stone 2, then 3, 4, 5, 6, and so forth, around the circle going counterclockwise. And there are certain alignments, and the alignments are described here. This is Easter Quarries in Scotland, and it was from a paper by John Hill. John Hill is a instructor, teacher professor, I should say, in England, and he's written a book on it. In fact, his book is available on, I saw it on the internet. I'm trying to think, the usual booksellers, but his book is available, and he also has some YouTube videos. So if you want to see a little bit about him, he'll talk about these alignments. And what was interesting about it is that there is a definite ratio between the length of the recumbent stone and the diameter of the circle. The recumbent stone, for example, in Easter, I'm hoping I'm pronouncing that right, Thor Quarries is 5-to-1. There are other stone circles that the diameter to the recumbent length is different, but that's basically one of the things that he found. And he felt that there were reasons for that. I'm not clear that it's that I know what they are, but they may have had something to do with the ceremony. But there are alignments that he shows between solstices and the moonrise. When he says winter moon set, as you are undoubtedly aware in astronomy, you know the winter moon set's not in the same place. So it has to be one of what they aligned to was one of the standstills. There are 2 standstills. I don't know if everybody's aware of that, but the standstills are to go from one standstill, like a minimum standstill, back to that same minimum standstill is 18.6 years. And some of these alignments were to either one or both of the lunar standstills. Another thing that she brings up in her book is Warren Field in Aberdeenshire. And Aberdeenshire, this field has 12 holes that have been dated back with, there's carbon dating that they were able to get back 8,200 years. And so the holes themselves are aligned for viewing the moon, and they're the way they have it. I'm not totally clear on how the lunar alignments work. They had one of the alignments was to recalibrate this once a year to the solstice. So the solstice arisal is lined up to a spot between the mountains. And anyway, there's some details on this as being one of the early calendars. It predates even the Babylonians, and it predates farming in that area. This was hunter-gathering society. So it was interesting that if they were hunter-gatherers, why would they need a calendar? And the answer may or may not, we don't know, but the answer may have to do with whether there were fish runs that started at some time or whether they needed a calendar. There's a pretty good thing about the calendar on WikiLeaks, Wikipedia. I'm sorry, WikiLeaks. I'm thinking of the spies. I'm out of my element here. Another thing she brought up that I was not aware of before was this Nebra disk. The Nebra disk is, there was a couple of guys, there's an interesting story with it, that they were illegally digging in Germany near the town of Nebra. They were out in an area they weren't supposed to be, but they basically went ahead and were digging up these, they were looking for World War I, World War II stuff, and they came across this. And this Nebra disk was considered to be one of the oldest known representations of the cosmos. The next slide shows it in more detail. I need to move there we go. And the Nebra disk, this center area here, are you seeing my mouse?
Yes.
Okay, that area right there was thought to possibly be a representation of the Pleiades. There's 7 stars here, and the Pleiades is sometimes called the 7 sisters, but only 6 are visible. So I don't know if maybe a few thousand years ago there really were 7. Why did they call it the 7 sisters? But the angle that was 82 degrees here is the angle at that latitude, at the latitude of Nebra, is exactly 82 degrees between the summer and winter solstice. So one of the people that this Professor Wolfhard Schosler claims that was because it was aligned for the solstices, and that it was one of the first astronomical measurements or instruments that was available. And it's basically goes back to the Bronze Age. It doesn't go back nearly as far as the calendar that I mentioned. But these are things that were in that book. And I think you'll find the book, I'd recommend it. I think it's an excellent book. And it's called Our Moon. My second author is Isaac Asimov. Most of you probably know of him. He probably wrote more books than any other living or non-living human being. He has over 500 books. I don't know how he managed to do that. I couldn't read 500 books, much less write them. But he's an interesting character. I met Isaac Asimov, and that was one reason I brought him up in here, because I've enjoyed a lot of his articles. And this was a our second cruise and our second trip to a solar eclipse was in 1973. We brought our kids along and we went to Africa, and some of the people on board are in this picture. Scott Carpenter on the left, Frank Brandley, who was an author, Isaac Asimov, another author, Walter Sullivan, and Neil Armstrong were pictured at the table in the front. And this is the ship we were on. And this was actually his Asimov's first eclipse. It was our second one. And he described it here. The sight of the total eclipse was wonderful. I was excited enough to be shouting wildly at the moment of total eclipse. One explanation was, yes, that's it. That's it. That's the way it's supposed to look, as though I was congratulating the cosmic director who was running the show. The other was when the brighter stars became visible. That proves it. The stars do shine in the daytime. The whole thing was a spectacular success. And of course, if you're an eclipse chaser, and I am, I guess, since this will be, my next one will be 19, I have to say, I agree wholeheartedly with his statement. We're already got our next eclipse planned. We'll be in Spain for the 2026, if we live that long. I saw Isaac Asimov one night at dinner. I saw him eating by himself and he was having his dessert. And so I thought, aha, time to catch him. So I buzzed over to his table, sat down and asked if I could join him. And he said, of course. So I talked with him for a while and asked him if he knew about Destination Moon, the movie. And he said he certainly did. And we had a very interesting discussion of Destination Moon. In 1950, I was a paper boy. Guess I'm dating myself a little bit. One of my customers was the projectionist for the State Theater. So I would take my newspaper to him. I got in that day and they were playing Destination Moon. That's how I remember seeing it. I never went to the theater at night or anything. So this was one chance to see the movie. I watched it and my customers got late papers that day because I got hung up watching it. It was really an interesting movie. Isaac Asimov on board, he had some books and I bought a couple of them. And one of them is the early Asimov. This is science fiction and it's short articles. I enjoyed it very much. I would recommend it to you if you can find it. Any of these books that you do find, you're going to not pay very much for because you can't buy them new hardly. But this is called the early Asimov. I like the cover. He has his ears between space, so it looks like his brain is spaced out. Another book he wrote was Today, Tomorrow, and so forth. These are essays that had been previously published. And again, Today, Tomorrow, and doesn't say whatever else it is. But the first essay he wrote is entitled something about the platypus. I think it was called, I think I wrote it down here, forgot. What do you call a platypus? And the interesting thing about what do you call a platypus is that's going to be one of the animals that Rebecca Boyle talked about in her, she didn't talk about the platypus, but she talked about the developments. And I thought Isaac's talk about the platypus kind of connected some dots between reptiles and mammals. So that's why I was interested in his story. Another story that was in here, I just read recently, he wrote it in 1968. The book was published in 73, but the article that he has was 68. And it was about computers of the future. And I thought, that's an interesting idea to see what they thought in 1968. Because we had, at the lab, we had just graduated from Frieden calculators to the latest electronic 4-function calculator. And computers, yes, the lab certainly had computers, but they were more in tune with what a fairly sophisticated computer calculator could do today. And so it was interesting to read that. And by the way, he predicted AI as one of the predictions he made in his article. He also predicted that humans would be back in the moon in force, mining factories and so forth by 2019, which of course did not happen. But I snagged this image of what a lunar station might look like, and he had predicted that we'd be doing that, that we might even be beaming solar power back to Earth from solar power stations. I think he was a little overly optimistic on both of those scores. Another book he published was called The Tragedy of the Moon. When I saw that, I couldn't help myself. I had to buy it, so I got a copy of it. And I thought, I wonder what the tragedy of the moon was. Well, he brings up a few points. The book is actually, The Tragedy of the Moon was actually only his first essay in that book. It's another collection of essays. And it turns out that it really isn't that tragic, but one of the things he felt was that if the moon had not gone around the Earth, but instead had gone around Venus, things might have been different. The Greeks wouldn't have had a heliocentric view, and it might have speeded up our development, because for many years in the Middle Ages, we were sort of stuck. And he felt that that was part of the tragedy of the moon. And his question, what if the moon went around Venus instead, is an interesting one. Earth would have a perpetual moonless night, good for astronomers, at least those who aren't looking at the moon. The brightest object in the night sky would be Venus, and our moon would be about as bright as, I can't read my own deal. I think it was Arcturus, wasn't it? Can't read. Oh yeah, Arcturus. During the time Venus is an evening star, the moon would make 8 revolutions around Venus. So it was clear that the Earth was not the center, and we would have known that information much sooner. Heliocentric model may have been established thousands of years earlier. And as you guys know from our discussions on ancient astronomy, there were Greeks that actually thought that the moon was, that the heliocentric idea was put forth by Aristarchus, who was a Greek astronomer early on. And it might have enabled the discovery of Newton's laws and enabled science and religion to live in harmony. That was his other point. So the tragedy of the moon was the first chapter. The second chapter was called The Triumph of the Moon. And I thought there were some interesting points he makes for the development of life on Earth. Life began in the water, and it may have been a tide pool, and it included bacteria, algae, jellyfish, and so forth that we've seen dated back to 2.5 billion years ago, according to Isaac Asimov. His date does not comport with dates that have been since he wrote that about 50 years ago. There's been an update, and that's more like 3.5 gig years now. Trilobites appeared some 500 million years ago. The tides stranded a lot of marine life on land, and the significant higher tides may have, they went for millions of years, left some marine life vulnerable, dried out, and die in the tide pools. But it was this that may have contributed to the evolving of life forms that could live without water, and ultimately to humans. The tides in the early Earth were very, very large. There was probably more like tidal waves because the tides on the Earth are the tide on the Earth to the moon is 81 times stronger, but the tidal effect also put a brake on the moon's rotation, and so it probably contributed to tidal locking the moon to the Earth so that one side always faces us. And tides also had a significant impact on erasing the early history of the Earth. We probably had more cratering, especially large cratering, than the moon did, but all of that got erased, and a lot of it probably got erased by these super high tides. The tidal effect goes much higher with distance. So if your distance is half, the tidal effect is 6 or 8 times more than it would be. It's not inverse. Asimov did not discuss the early fishes, but this is one thing I thought was of interest that I was finding when I was doing some research on it. And there are a series of fishes that developed lungs. This is the Australian lungfish. It has a single lung, and it has front fins that got very strong, and it could propel itself along in sandbanks and so forth. So it could live out of water for short periods. It basically wants to be in water and it wants to use its gills, but it has the ability to live out of water. So it might have been one of the connections between life moving out of water, which it started in, and all the early fossils were in water. And it might be a link to the tetrapods or the four-footed animals. The second development was our brain size and ability to reason. My apologies to Larson for this one. I sort of took his idea and redrew it. I have to say I copied his caveman, but fishing for Pisces in a lagoon is best from new moon to first quarter. But we were learning to count and to reason based on the fact the moon was available. Early man also probably observed solar and lunar cycles. We know that we see enough things like the calendar of Warren Fields that I mentioned, that the calendar was important to early people. And a new moon starts approximately every 29.5 days. It is not exactly 29.5. There's a few hours plus or minus one way or the other. And the few hours are due to a couple of factors. I can give you one of the factors. For example, at new moon, the moon is closer to the sun than it is at full moon. It's on the opposite side of the Earth. And you're really dealing with a three-body problem, including the sun. Three-body problems are notoriously hard to calculate, but that is one of the factors in having the 29.5 is not an exact number. Another factor in the time is the fact that the moon's orbit is not perfectly circular. It's a little bit of an oval. And you can recall Kepler's second law that says equal areas and equal time. And that basically implies that the moon will move faster when it's closer. And so as gravity affects it, it moves faster and slower, and that also affects that time. To develop our reasoning ability, the moon, we needed to count and measure, and part of that had to do with counting new moons. Another factor was not mentioned by Asimov that had to do with counting, but this was found in France, and that was this antler that appears to be counting cycles in the moon. And if you look carefully at it, you see some of the notches have the appearance of moon phases. Eclipses of the moon, we know, went back very far. The Chinese, the Babylonians, and the Greeks. A lot of that had to do with astrology, not astronomy. This is a picture I took of a lunar eclipse, so I'm kind of proud of that picture. Came out good. But lunar eclipses were another thing that people wanted to count, and so it developed some of our ability to do counting. The Greeks even went further than that. They started working on trigonometry and how far is the moon and so forth. And in 150 BC, Hipparchus of Nicaea had correctly determined the distance to the moon. And he did that by looking at shadows in wells that were two different distances apart, a long ways apart. Hipparchus just determined the length of a year within an accuracy of 6.5 minutes. It's unbelievable that he could have done that with the primitive materials they had, or observation. They didn't have telescopes to calibrate things and good clocks and so forth, but he got within 6.5 minutes is what I have read. One of the things that you may want to find more information about the obliquity is the ability to see the changes in the angle, but it was measurements themselves that gave the ancient astronomers an idea of the immensity of the solar system. And summarizing his key ideas, here they are. Triple triumph of the moon was it made possible for man to exist because of the fact that it stabilized our orbit, or our angle, or our obliquity, the tilt. It made it possible to develop math and science, starting with counting, and it made it impossible to transcend Earth and conquer space. The second area, that's basically as much as I'm going to talk about astronomer or authors, move to the astronomers. It turns out their astronomers and authors have a lot in common. The first astronomer is Maria Zuber, and she has also authored, I don't know, several hundred papers. It's an amazing number. She was born on June 27th, 1958. And if you're wondering why I put that on there, it was because I noticed that she's born on my birthday, but I was 19 that day when she was born. So I guess I got a few years on her. She is a vice president for research at MIT. Makes me feel like a complete failure in life. But with her work, she was the lead investigator for the gravity investigations on the moon, GRAIL. She's also studied the Earth's tilt. She says in her comments, the obliquity has changed less than a degree over thousands of years. And if we didn't have a moon, it would not be stable, leading to dramatic climate changes. By comparison, Mars has had a wide variations in obliquity. I think it's because of precession. I'm not certain of that, but I believe that's it. A study of Martian obliquity has varied from 15 to 35 degrees over 120,000 years. The effects of obliquity changes are dramatic, and this is a simulation done by computers of how the Earth's obliquity of 23.5 degrees, what would the temperatures be was the question if our obliquity was 54 degrees. So they ran these computer calculations, and the results are that the top one shows what it would be in the winter, and the bottom one shows what it would like in a North American summer. The temperatures notice in Asia are up somewhere in the neighborhood of 170 degrees Fahrenheit. No one could live in a temperature like that. In the winter, notice what the temperatures are in the winter. The dark blue area is roughly 30 below zero Fahrenheit, or 70 something degrees. Oh, I'm sorry, let's see, I had it over here. 40 degrees below in centigrade is equal to 40 degrees below in Fahrenheit. So the whole of the United States would be very, very cold. I thought that was that came from a website that was, I'm trying to remember the website. I'm sorry, I might have it on my notes. I don't see it on my notes, but I think you could find it if you're interested in. The Gravity Recovery and Interior Lab, I discussed this a little bit in a previous talk, but there was other things that have happened since, and I wanted to share it with you what I found out. There were 2 satellites with GRAIL that communicated with each other with microwave frequencies and back to Earth. The change in speed was due to the fact that the angular momentum changes as one satellite went over a gravitational anomaly, or say a denser area of the moon. And that would cause a Doppler shift in frequency of the radio signals. I'm not sure if everybody knows what a Doppler shift is. Oh, okay. All right, I'm taking two tuning forks. Where's my camera? There.
And we don't hear it.
You don't hear that?
Nope.
Microphone does not.
Microphone, we have a microphone.
I'm sorry.
We have a camera. Here we go.
Pretty obvious when you do it like this by your ear and you can hear the change in frequency. That's Doppler shift. But Doppler shift does not have to be sound. It can be microwaves or radio. In fact, that's what Doppler radar does. And so the change in speed of the satellite is related to the gravity. And so GRAIL basically recorded the change in speed, and then that's what they did with their data, is to reduce the data is to figure out what the gravity looks like. Did that make sense?
Yeah.
There was a similar idea that was done for the Earth, and that was called GRACE, and that went for quite a few years. By the way, GRAIL ran in 2012. GRACE was a long-term thing, and they measured a lot of the gravitational variations of Earth with GRACE. The other thing that Maria Zuber did was she led the analysis of the Lunar Reconnaissance Orbiter. And I thought Lunar Reconnaissance Orbiter was just mapping the moon, but it did more than just mapping it, because it also has spectral cameras on board that, by looking at the spectrum, could determine different types of rocks, including the difference between ilmenite and normal basalt. There's a difference in reflectivity, and the reflectivity difference is a function of the wavelength. Sort of interesting point. Here is a visible picture of the moon, a topography of the moon, and a gravity map of the moon. Same image, or the same area of the moon in all three. And that the gravity map, the red is lower density, and that's where the piles of material that were evacuated on the craters is. So these are craters, and the red area is the lower density, or excuse me, the higher density. The lower density was blue, according to my list here. There's kind of an interesting sort of a area around the gravity map at the outside that looks like dikes or something along the outer edge of that long area. The GRAIL indicated that lunar mascons were generated from impacts on the ancient moon when its interior was much hotter. The moon's light crust and dense mantle combined with the shock of a large impact created mascons. And mascon was a mass concentration, is what that stood for. Here's some more GRAIL results. I don't know why they looked a little bit different than the other, but I picked these off from NASA, this particular image. There's some straight line areas on GRAIL that appear to be buried lunar dikes formed by magma that may have been seeping into fractures, and they wound up as dense walls of rock. It may be evidence for early expansion of the moon. Here's another one of the areas right here, and where the dots are. That is a gravity gradient versus topography. You don't even see it on the topography other than the fact that they've put little circles on there to show you where it is. But that's a difference is what GRAIL showed versus a topography map. With GRAIL and the LRO, scientists were able to measure the tides on the moon, which gave an overall value of the stiffness of the moon. And that was another one of the factors that's relatively new that had not been done before, or at least I didn't discuss it in my previous talk. The other point here that was, I think I'll read it off of here. The Earth is 81 times more massive than the moon and 4 times its radius. As a result, the tidal force of the Earth at the surface of the moon is 20 times stronger than that of the moon on the Earth. So we do see a tidal impact from the Earth to the moon, which is very strong. GRAIL results were cited as a hypothesis to account for significant differences between the near and far side geology. More on that later. This was one of the points about what GRAIL did that I was not aware of. Right here in the middle shows the gravity anomalies that could be interpreted as material that was dense and sank in the interior. And this material was probably ilmenite. Our analysis of the models and data tell a remarkably consistent story. Ilmenite materials migrated to the near side and sunk in the interior in sheets like cascades, leaving a vestige that caused anomalies in the gravity field. One of the things, by the way, I forgot to mention back here, if you were wondering on that, on this picture, which I drew this, by the way, but I was thinking in terms of another thing I could have done just as easy. If any of you ever played tetherball as a kid and you try to run a ball around the post, you know what happens when the ball is getting close to at the end of the session, whoever's winning, the ball is going really fast at the end. And that really shows an evidence. That's a good example of the conservation of angular momentum. And by the way, angular momentum, there's two formulas for angular momentum. The one for planets is very simple. It's just linear momentum, which is mv times the radius. And so a change in mv times the radius of wherever that is the change in angular momentum. And because of conservation principles, the angular momentum doesn't change, but if it's, and that's what GRAIL was doing. Basically, if I wrote L1 equals M1 V1 times R1, that I could then say equals L2 M2 V2, and you see that the only variable there is the velocity. I don't know if I made any sense. I probably didn't. If I didn't, just ignore me, which you probably did. Oh, this is William Hartmann. I like the fact that he was born same month I was, 1939. And he's a planetary scientist. He went on to accomplish great things. He wrote the history of the Earth, which I really like this book. He's got beautiful illustrations in it. He also is a scientist, and he's famous for a couple of things that he's done, but namely, his most important contribution was the proposal of the giant impact theory, along with Don Davies, which was a person that had gone to school with him. This is one of his drawings, and when you think about all of the impacts that occurred early on in the first 50 or 60 million years of the moon's existence, it must have been a shooting gallery. And there were huge plasmatoids that were running around like this. And this was a idea of what that must have looked like from Bill Hartmann's drawing. I wanted to share a little of his art with you because it's really nice. And again, the book I just mentioned, History of the Earth, has a lot of his art. He has some other books that I have also that have his art. This one, I like this because it had a appearance similar to one of the early artists. I'm forgetting his name. Idea here. This is Hartmann's drawing, but the rocket kind of looks a little bit like one of the original artists that did that. Another one of Hartmann's drawings. And here is one of his drawings showing what he thought the impact of Theia on the original formation of the moon must have looked like. By the way, the Earth prior to this was called Gaia, which is the Greek goddess of the earth. And Theia was the mother of Selene, and Selene was the goddess of the moon. So that's where the names came from. When Bill Hartmann was a graduate student, he studied under Gene Kuiper. Kuiper was pretty famous for his comet, and one of the major belts where comets are is named for him. And he had a suggestion because they had an area nobody in 1962 knew what the backside of the moon looked like, but they had a crater that looked like you could just see pieces of it. And so they projected the flat photo on the left was projected onto a sphere or a hemisphere on the right. And you could suddenly see the fact that there's a ring structure, and that ring structure. So Bill Hartmann, they published a paper saying that it looked like there was a massive crater there. Turns out it's the largest impact crater on the moon. Orientale, and it is not really visible to us on Earth. It only really shows up in space. You can see it on, of course, with the lunar LRO, we've been able to see good pictures. In fact, the picture I opened the slideshow with was Orientale. He came up with this idea of the collision, and it's described things that a moon's formation should account for. At one point, there were at least 4 ideas of what the moon was, how the moon was formed. There were several. And so in order to eliminate which ones are not good theories, this is a list of things that it should have to do. It has to have chemical composition, show why are the composition of moon and earth rocks similar, but there aren't volatiles on the moon. Why did the moon not have volatiles? Speed and inclination of the moon's orbit, the differences in the moon's near and far side. In fact, the moon's core is much smaller than the Earth's, the large size of the moon compared to the Earth, and any of those theories that are trying to explain the moon should answer those questions. There's a report card that was made up. In fact, it's in a book called The Big Splat. And The Big Splat by Dana McKenzie has a report card in it that gives grades to each of the areas that I mentioned, to the different theories. And it explains why the only theory that really doesn't have a failure someplace is the giant impact. So the giant impact explains why the lunar rocks are similar composition to our mantle, because really they're saying the moon formed from our mantle, that when the impact occurred, our core had already differentiated. And so most of the material that went into space was from the mantle. The giant impact would have happened after the core had formed, so it's consistent. The moon may have experienced a higher rate of impact heating and therefore a deeper magma than Earth. And a giant impact explains the high angular momentum and obliquity. The moon also has a almost identical oxygen isotope ratio on rocks as the Earth. And that really kind of points to the fact that they had to be close together or almost one and the same at one point in time. This is a simulation. I believe this was done in Kansas. There's a bunch of people now that have taken up simulating the impact. I don't know why this one, I've downloaded this, but it doesn't begin at the beginning. I'm going to play it and you'll see that it's already happened. So it's like you walked into a movie halfway. Okay, here's the beginning. This is the start of the simulation. I think you got the idea, so I'll move on. There's another thing that is recent, and this was one of the things I first saw that I got inspired to try to find out what all's been going on. But there are two continent-size blobs of material that are near the center of the Earth, beneath Africa and the other beneath the Pacific Ocean. The blobs are twice the size of the moon, and research in the last decade has shown they're likely composed of different proportions of elements than the mantle itself. These blobs are called LLVPs. LLVP was for large, low velocity provinces. Where did they come from? A new study was done at Arizona State, another one at California Institute of Technology, indicated that the blobs were remnants of Theia. I asked Dr. Hartmann about his thoughts about that, and he responded as follows. It sure looks like something's been detected. I don't feel competent to judge, but my first reaction is the impactor would be pretty well destroyed during the impact. The blobs may be, here's a simulation of the blobs. That this is the gray area is the mantle of the Earth. And the blobs are these reddish things hanging around there based on earthquake data. The result of the impact on Earth left the Earth and moon molten. Heavier elements, primarily iron and nickel, migrated to the core under the influence of gravity. Iron took on with it many hydrophile elements. A hydrophile element is one that's attracted to iron, or that is easily combined chemically with iron. The iron and the other dense elements that are found in the crust probably arrived later from meteorites, not part of the original. My second astronomer will be much shorter on the next ones, is Stephen Desch. He's a professor of astrophysics at Arizona State. He wrote a paper and I had read it, and I was wondering when I read it if perhaps he had done what his work was. So I wrote him an email. He suggested that Theia was absorbed in the young Earth and left the blobs. And I said, the moon, I asked him about it, and his response, he said, the moon appears to have materials within representative both the pre-impact Earth and Theia. It was thought to be remnants of Theia in the Earth that would have been erased and homogenized by billions of years of dynamics, mantle convection, and so forth. It was the first study that anyone had done that showed that pieces of Theia may still reside in the Earth. And I asked him about the computer simulations. He said there were not new simulations. I wondered if he'd been able to simulate the formation of the blobs. And he said just a synthesis of previous, he didn't do anything that showed the synthesis of the blobs. He mentions in here deep mantle plumes are much lower in the DH ratio. D and H ratio is deuterium to hydrogen. And by the way, deuterium to hydrogen ratio is really important in astronomy because it tells a lot about where something came from. So for example, water is H2O, as everybody knows, but if it has deuterium in it, there's a ratio of deuterium to hydrogen. And the DH ratio if we look at just the oceans and the DH ratio, we can find out where was the most likely source of the water from the ocean. And it turns out that the DH ratio is quite sensitive to where it came from. This is, again, another showing of the impact creating the blobs are shown, or at least I think that's supposed to be the blob on the right, but the mantle was not totally melted by the impact. So the blobs from the iron-rich Theia may have stayed in the mantle, deep mantle. And Caltech has also reached that similar conclusion to the Arizona State result. These are fairly recent studies. Our next astronomer is Robert Canup. I brought her up in a previous presentation, so we'll move along with it. She was the editor for this book, Origin of the Earth and Moon. There's 29 technical articles written by 69 contributors. And by the way, Bill Hartmann was one of the authors of an article in there. His article had to do with cratering and the size of craters and when they occurred and so forth. All of the articles in this book are very technical. I bought the book because I was interested in it, but I'll tell you, it's not for the typical average reader that just wants to get a basic idea. I would not recommend it for that person. This is really written for astronomers or people that like mathematics because it's pretty mathematical. I wrote her an email and asked her any of her simulations. She was one of the ones that did early simulations. If the LLVPs came from Theia, her response was, I don't have any simulations showing a Theia LLVP connection. I think it's interesting, but somewhat speculative, definitely worth a follow-on model. So that was her response. Both the moon and the Earth are presumed to be made of three components: the pre-impact Earth, or the proto-Earth, also called Gaia, the impactor, which causes differentiation, and a late-stage veneer that brought additional hydrophiles. Moving to my times perspective again, now the width of each square is still 100 million years, but we'll look up at the green square. And the accretion of the planets, these are now 1 million year old squares. All of the planets were done that first time frame. Keep in mind the dark green area. They're used in the next slide. The impact that hit the moon is down here. And this is, again, still in that first 100 million year block. I kind of think it helps me visualize time when I do it like this. I give apologies to Bill Hartmann for using his idea, but that's the way he showed time in his book, and I thought it was really good. So I put the little green blocks down here so you could kind of visualize where this was. And this is based on Robin Canup's book as to when planets were forming, when they accreted, when the iron core was accreted, and so forth. By the way, the article is one that you can download online, that particular article. Robin does a lot of studies, part of which I mentioned. There's several areas of study that she does, as do many astronomers. Isotope ratios, which really, I learned a lot about isotope ratios. There's a whole chapter in here on her book, or more than one, discussing isotope ratios and what you can learn from that. There's also computer simulations, which is another thing she's done a lot of. And finally, one of the most important areas is on meteorites. Meteorites have many meteorites. This is a stone meteorite called Northwest Africa. That's what NWA was, 869. I happen to have 3 NWA 869s in my collection. And it has a lot of inclusions. Some of the inclusions are CAIs. Those are called calcium aluminum inclusions. And this particular meteorite, I don't know if it's the same parent body in all cases, because there's been 2 metric tons of it that have been sold in Morocco and around the world. I have one I could put up to show you on the screen. I think what I'll do with mine, I'll let it go. I was going to share it with you, but I think I'll pass and say the picture here is probably as good as you're going to see from what I show you. But I really like chondrites, and I also have a carbonaceous chondrite, and I was going to share that. But in carbonaceous chondrite, the chondrules are very, very small, and I don't think you'd be able to see them. But a carbonaceous chondrite has a very dark matrix at the back, and that's because of the carbon. And those are considered the oldest type of meteor in the world. This is a Brannan meteor, and it has some interesting chondrules. But this isn't really, I'm sorry, I said that wrong. It's not really a chondrule. These are, this is the interface between the mantle and the core of an asteroid that is broken apart and landed on Earth. There's a number of these around. When they do a slice of them, sometimes they have some very interesting olivine crystals and so forth in the center. I happen to have one of these. I don't have one that big, or it'd be pretty expensive if I did. This is a little bit on the formation of the solar system and when was the creation of planets, and when did the impactor occur, etc. One of the things that I was going to mention is the disk itself in the second picture here. Probably started to differentiate into rings. It was Kant and Immanuel Kant and Laplace in France had done work on the idea of a disk, and it wasn't until 1950, and it was Russian. I'm trying to think of his names. Again, I have it in my notes, but I kind of got out of my notes here. Oh, here it is. Safronov, Victor Safronov. He showed that disks could not be stable if they were homogeneous, and that they would start forming rings of structure, and the rings themselves became the planets. So I thought that was kind of interesting. There's been a lot of work on aggregation theory. How did it happen? How does some little tiny thing, I can tell you in our house, dust bunnies seem to form very easily. I don't know if that's what was happening at the beginning, but material that was in that initial disk formed into the eventually formed to planets because of these tons and tons or trillions of pieces of material that were wandering around. I have a riddle for Ray, maybe he could answer. Why are chondrites lousy mathematicians? Ray may not answer. I'll give you the answer, Ray, so you can use it at the next Astronomy on Tap. They can't differentiate. That's an astronomer's joke. If I made it up myself, it's probably obvious. Hope you liked it. Okay, a lunar impact. Why were the front and back sides different? I've asked that question of different people, and I think one of the answers that I think is probably logical, there's a 2019 paper that was written. It said a huge impact on the moon on the front side could have thrown material that wound up around the moon and built on the backside. So I've asked some people about that, and the key points from that study were that the giant impact on the near side of the moon can create an asymmetry between the near and far side. Lunar lowlands and crete materials. Crete, by the way, if you're wondering, is potassium, rare earth, I forget. Potassium is the last one. Materials that the creep materials can be easily picked out, and they're actually shown on this picture. The giant impact predicts the moon has a significant 182, that's tungsten, W182 is tungsten, anomaly after the formation expected by the collision formation of the moon itself. Quickly about the formation or the future exploration. This shows the locations of all the Apollo landing sites. It looks like we're further, like 15 is further north, but if you look at it on a globe, these are all relatively close to the center, the equator. We don't have any samples from the poles or near the poles, and that would be one of the things that would be really important for future exploration. And finally, NASA has its own moon dreams, and that's the idea of a new mission. It's called Artemis. NASA has 13 regions that they're thinking about for Artemis 3 in a couple of years from now. And most all the 13 regions are fairly close to the South Pole. And it may be that we will be able to pick up things like water and volatiles that have been in there for billions of years. So it would be a real interesting return of what we get from Artemis. By the way, question is, are there any resources we can use? Certainly water, for obvious reasons, especially if we want to go on in space to Mars. This might be a place to get some water. Oxygen, although there's no oxygen gas on the moon, there is oxygen available in rocks if we can get it chemically out of there. Also, one of the things that's really interesting, there's an article in the Earth on the absence of xenon on the Earth. We are very, very low in xenon, and xenon is the heaviest of the noble gases. And xenon on the sun is higher than it is on the Earth. And we formed from the solar nebula. Why don't we have more xenon? So there's a xenon problem. But what that basically says is, as we formed as a planetesimal, we probably didn't have, the planetesimals didn't have enough gravity to hold any of the noble gases. And so they escaped. And probably that really says that the moon doesn't have noble gases either. And that may go along with this impact theory. So that's basically my presentation. Sorry I went a little long here. Looks like I should have tried to end it sooner, but that's all I have. If there's questions, I'll be happy to try to take them.
You had good information, Dave.
I have a question. Why is going to the poles on the moon important?
Well, two things. The poles possibly have ice, which would be a resource which would be very important. There's a crater or two that has never seen sun, and I think LRO detected ice in those craters. So that's one of the reasons. The second one is we don't really know if we have pristine. Most of the collection of rocks that came back from the moon were less than 4 gigayears old. And you say, you know, that's pretty old, but the moon's 4.6 gigayears old, according to other sources. And so there might be more ancient rock in other locations, and that's one reason that we need to be in a location that we can still beam radio signals back to Earth. They don't want to put an astronaut on the far side at this point. I think it'll happen someday, but Artemis is not ready for that. Other questions?
Now, I heard a long time ago that the explanation for all those craters being on the back of the moon and the front of the moon having all the seas because the Earth was blocking the bombardment of the face of the moon as opposed to the back. That apparently isn't believed anymore.
I don't believe that because the moon itself would present different faces to the nebula, and there's a lot of cratering on the backside also. There's a paper that Bill Hartmann wrote that I think really kind of says a lot. He said, stochastic does not equal ad hoc. That was the name of his paper. Stochastic does not equal ad hoc really means stochastic is randomness, and ad hoc is kind of a made up theory. So random events, there are random events that have occurred. We know that. For example, Uranus is tilted 90 degrees on its axis. Something gigantic must have hit it. Why only Uranus? And then if you look also, Venus is rotating the wrong way. And so, or at least not in the direction all the other planets are. Why is that? And again, that's a question of some random event that happened. So I think his point was that we can't predict the fact that if a very high impact event occurred on the near side of the moon, why it didn't happen on the other side. And it's, well, you can't have it on both sides at the same time. So it's a random event, I think, is what that was about.
If we were looking for parts of Theia that were not absorbed by the mantle of the Earth or the core and didn't form the moon, where would we be looking?
I would think the crust, there was a late, the crust of the Earth is not where we would look. And the reason is because there was a lot of impacts that occurred after the moon had been formed. And so a lot of what we have today for hydrophiles that are on the crust came from a late bombardment. Moon had already been formed. So the only place that I can think that we would see any parts of Theia are in the mantle, and we can't drill into the mantle. So the only way you could really see the mantle material is when there are deep volcanic sources, volcanoes that have gone significantly below the crust with their source for the lava. I'm not enough of a geologist to say how they know that, but we do know we do get mantle rocks from lava. And that's the only way I think we see it.
I'm actually thinking about parts of Theia that didn't stay with Earth.
Oh, you're the stuff that went out into space. I think that is probably has probably impact. Well, that's an interesting question. I don't know. I don't want to try to speculate, but I don't know.
Other questions?
One last question or comment. I saw an article a while back on the formation or one of the simulations of the formation of the moon. And one of them came out and it showed Theia impacting and then the blobs of debris coming off. One of them formed the moon. Another one, they showed a secondary piece of small moonlet right behind it. And they're theorizing that one of the reasons for the thickness difference of the crust on the backside was that this blob eventually did kind of a slow motion collision with the moon, kind of spreading out on the backside there, causing the thinness. I don't know.
That
if
may
you-
have had something to do, I think what you're suggesting is that that would be the anorthites that wound up as the major component on the backside, correct?
Yeah, change the thickness of the crust on the
Yeah,
backside.
and that would have been a lower density. The average density on the moon is 3.3 grams per cubic centimeter, whereas on Earth it's 5.1, which also states, that also kind of talks about the fact that the mantle itself is much denser, as is the core on Earth, than the moon. But what went on the back was probably anorthosites. I think I'm saying that correctly. I have a piece of it here, as a matter of fact, but not lunar anorthite. I have some that was Earth. I have a collection of rocks that I think I shared about 5 or 6 years ago that are a collection of rocks similar to the ones on the moon. In fact, I was going to share a piece of ilmenite tonight, but I can just tell you it's kind of a dark, not very interesting piece of rock, but mine happens to be attracted by a magnet. I've checked that. I thought, I wonder if this thing is attracted to a magnet, and it's slightly magnetic. Its chemical formula is FeTiO3, iron titanium oxide. That's ilmenite. But the backside of the moon doesn't have much ilmenite. That's in the front side. I don't know if I answered anything, but I think
You know, I just was saying that theory accounted for the thickness.
I have
difference.
seen that theory that you're referring to, I think, and that's a relatively recent theory.
Yeah, it was there's an article about one of the simulations they did kind of pointed to that. One of the mass supercomputer simulations showed something like that could have occurred. And that was one way to maybe account for the thickness difference.
Yes, great.
Let's thank Dave.
Okay, thanks very much. I'm gonna depart. It was good to be in Grass Valley for a little while, even if it's virtual. Would have been better if I could have been there, but airplane tickets are expensive, so I didn't do that. So
Thank
Will-
you.
you bet. We'll catch you at the next one.